How can something that explodes violently in water also be the very substance your body cannot live without? This is the paradox of sodium. It is a story of two opposing forces held within a single element. On one hand, it is a volatile metal, capable of sudden and fiery destruction. On the other hand, it is a quiet, essential partner in the dance of life itself. Sodium is the soft, silvery metal that bursts into flame upon contact with water. The salty taste of the ocean, the crucial ion that makes our nerves fire, the ingredient that has preserved our food for millennia. This is a journey into the heart of that paradox, exploring its chaotic power and its life-giving necessity. We begin with a simple, almost magical act. A small, dull chunk of metal is dropped into a bowl of clear water. Instantly, it skitters across the surface, hissing and releasing a trail of white smoke. It spins faster and faster, a frantic dance of chemistry. Then, with a sudden pop, it erupts into a brilliant yellow flame. This is sodium revealing its wild side. Now picture the vast rhythmic pulse of the ocean, its waters rich with dissolved salt. Zoom in closer to the microscopic world within our own bodies, where electrical signals flash along our nerves. These signals are possible because of sodium. This element is both the fire and the spark of life. Its story is woven through the fabric of our world, from the geological formation of our planet to the daily function of our own cells, or ancient trade, modern technology, health hazard. To understand sodium is to understand a fundamental piece of our universe and ourselves. It connects the stars, the stones, and the self. The same element that can be harnessed in a nuclear reactor also helps regulate the steady beat of your heart as you read these words. It is a constant reminder that the universe is often not what it seems. The most dangerous things can be the most necessary. This journey will take us back in time to the moment this element was first isolated in a laboratory. We will dive into the atomic reasons for its explosive nature. We will travel across vast salt flats and deep into the oceans where it resides. We will explore its critical role inside every one of us and see how human industry has put it to work in countless ways. Finally, we will look at the debate surrounding its place in our diet and its potential to power our future. The story of sodium is a story of balance, a cosmic balancing act between creation and destruction, all contained within one humble element. For thousands of years, humanity knew salt. Salt was a treasure. It preserved food when there were no refrigerators. It was so valuable that in some places it was used like money. Roman soldiers were sometimes paid in salt, a payment called a salarium, which is the origin of our modern word salary. The year was 1807. The scientist was a brilliant English chemist named Humphry Davy. He was a pioneer in the field of electrochemistry, the study of how electricity and chemistry interact. He had a powerful new tool at his disposal, the electric battery. He suspected that many common substances, like salt, were actually compounds made of simpler, unknown elements. He believed electricity held the key to splitting them apart. In his laboratory, Davy set up an experiment. He took a common sodium compound, caustic soda, and heated it until it melted into a liquid. Then he passed a strong electric current through the molten substance. He watched closely as tiny, shimmering globules of a silvery metal began to appear at the negative electrode. They were like little drops of quicksilver. As soon as they formed, they would burst into flame as they touched the moisture in the air. Davy had done it. He had isolated a new element for the first time. Davy named this new element sodium after the soda compounds he had extracted it from. His discovery was a monumental achievement. It proved that electricity was a powerful force for breaking down matter and discovering its fundamental building blocks. It opened the door to the discovery of a whole family of similar metals like potassium, calcium, magnesium. The quiet, ancient world of salt had given up its fiery secrets. Why is sodium so eager to explode? The answer lies deep inside its atom in the world of electrons. Think of an atom as a tiny solar system. At the center is the nucleus, like the sun. Orbiting the nucleus are electrons, like planets in shells. Each shell can only hold a certain number of electrons. Atoms are most stable when their outermost shell is completely full. Sodium, however, has a problem. It has 11 electrons in total. 2 fill the first shell, 8 fill the second shell. That leaves one single lonely electron in the outer shell. This lone electron is the source of all the trouble. It is not held very tightly by the nucleus. The sodium atom is desperate to get rid of it. By losing that one electron, its outer shell becomes the one underneath, perfectly full with 8 electrons. This makes the atom much more stable, so sodium spends its existence trying to give that electron away. This drive to lose an electron makes sodium an alkali metal, part of the most reactive family on the periodic table. When sodium meets water, it finds the perfect opportunity. Water is made of hydrogen. Water is made of oxygen. The sodium atom eagerly gives its spare electron to a water molecule. This act breaks the water molecule apart. The reaction creates sodium hydroxide, a corrosive substance, and it creates pure hydrogen gas. The process also releases a tremendous amount of heat. That heat often ignites the hydrogen. That is the pop you hear, and the flame you see. It is the violent, rapid release of energy as sodium achieves its electron-donating goal. Because of this reactivity, you will never find pure sodium metal lying around in nature. It cannot survive exposed to air. It reacts with oxygen in the air. It reacts with water vapor in the air. The moment it touches liquid water, it explodes. It can only exist pure when protected, usually stored under oil or kept in a vacuum. In nature, sodium is always found in compounds, having given away its extra electron. The most famous compound is sodium chloride, table salt. Here, sodium has given its electron to chlorine, forming a strong, stable bond that holds them together. If pure sodium cannot exist in nature, then where did all the salt in the oceans come from? The story is a slow, geological epic that unfolded over billions of years. It began with the Earth's early crust, rich in minerals, including sodium compounds. As the planet cooled and water vapor condensed, the first rains began to fall. This rain was slightly acidic. It flowed over the rocks, acting as a slow solvent, dissolving minerals grain by grain. Rivers carried these dissolved minerals on a long journey to the sea. Among them were stable sodium ions. Once they reached the ocean, they tended to stay. Water could evaporate to form clouds and rain again, but the heavier salt ions were left behind. Over eons, the cycle repeated. Rivers delivered a tiny trickle of salt, and evaporation concentrated it. The oceans slowly became saltier. Today, they are a vast reservoir of dissolved sodium chloride. This process is not just a story of the past. It is still happening today. Every river in the world is carrying a small amount of dissolved salts to the sea. But the oceans are not the only place where sodium collects. In certain arid regions, ancient seas have dried up completely, leaving behind immense deposits of solid salt. These form vast, shimmering landscapes known as salt flats, salt pans. In other areas, underground salt deposits called salt domes were formed millions of years ago. They are mined today for seasoning our food, for de-icing our roads in winter. From the rocks to the rivers to the sea to the salt flats on land, sodium is on a constant journey. It is a fundamental part of our planet's water and rock cycles. While it may be abundant in the ocean, sodium's most intricate and vital role is played on a much smaller scale. Inside the human body, every single one of our cells is bathed in a fluid that is remarkably similar to seawater, rich in sodium ions. These tiny charged particles are not just passive bystanders, they are essential workers that power some of our most critical biological functions. Without the right balance of sodium, our bodies would simply shut down. Life as we know it depends on this element. It is the tiny electrical spark that animates our flesh and blood. One of its most important jobs is in our nervous system. Your thoughts, feelings, movements are all transmitted as tiny electrical signals that travel along your nerve cells. These signals are generated by a mechanism called the sodium-potassium pump. The cell actively pumps sodium ions out, creating a difference in electrical charge between the inside and the outside of the cell. When a nerve needs to fire, special channels open up, allowing the sodium ions to rush back in. This sudden influx of positive charge creates an electrical spike, an impulse that travels down the nerve like a wave. This is how you feel the touch of a hand or decide to take a step. This electrical function is also critical for our muscles, including the most important muscle of all, the heart. Muscle cells use a similar rush of sodium ions to trigger a contraction. It is the signal that tells the muscle fibers to tighten. The rhythmic, steady beat of your heart is orchestrated by a precise, repeating pattern of sodium ions flowing in and out of the heart's muscle cells. An imbalance of sodium in the blood can disrupt this delicate rhythm, leading to serious heart problems. The element that burns with a yellow flame is the same one that helps keep your heart beating steadily in your chest. Beyond the worlds of chemistry and biology, sodium is a workhorse of modern civilization. Its unique properties have been harnessed by industry to create light, produce goods, control nuclear reactions. These lamps work by passing an electric arc through a small amount of vaporized sodium metal. Energized sodium atoms emit light at a very specific wavelength, giving that characteristic color. While LEDs are replacing them, these lamps define nighttime in the modern city. In the chemical industry, sodium is a fundamental building block. It is used to make a vast range of chemicals and materials. For example, titanium, airplanes, medical implants. It is also used to produce soaps, detergents, dyes. The paper industry uses sodium compounds to bleach pulp. The textile industry uses sodium compounds to treat fabrics. Glass production uses sodium carbonate or soda ash. Perhaps its most extreme application is in certain nuclear reactors. In advanced fast reactors, liquid sodium metal is used as a coolant. Sodium has excellent thermal properties and transfers heat efficiently. It is pumped through the core, absorbing intense heat from fission. That heat is transferred to a water system, which makes steam to drive turbines. The paradox, an element that explodes in water, is used to safely manage nuclear heat. While our bodies need sodium to survive, the story in the 21st century has become one of excess. The same salt that was once as precious as gold has become incredibly cheap and abundant. The food industry has discovered that salt is a powerful tool. It adds flavor, it acts as a preservative to extend shelf life. It can mask less pleasant tastes. As a result, huge amounts of sodium have been added to processed foods that make up a large part of the modern diet. The problem is no longer getting enough salt. For many people, the problem is getting far too much. This hidden salt is everywhere. It is not just in obviously salty foods like potato chips, pretzels. It is found in high quantities in bread, breakfast cereals, canned soups, frozen dinners, cured meats, and fast food. Many people consume far more sodium than the recommended daily amount without even realizing it. This overconsumption has been linked to a major global health crisis, turning an essential nutrient into a potential risk. The primary health concern associated with high sodium intake is high blood pressure or hypertension. When there is too much sodium in your bloodstream, your body holds onto extra water to dilute it. This increases the total volume of blood inside your blood vessels. The increased volume means more pressure on the walls of your arteries. Over time, this constant high pressure can damage the arteries, heart, and other organs. It significantly increases the risk of heart disease, heart attack, stroke. This has sparked a long and ongoing debate among scientists, doctors, and public health officials. How much salt is too much? What is the best way to reduce sodium intake across the population? Health organizations advocate for clearer food labeling and for food manufacturers to voluntarily reduce the amount of salt in their products. The advice for individuals is simple but can be challenging to follow. Eat more fresh, unprocessed foods like fruits, vegetables, read nutrition labels carefully, use herbs and spices for flavor instead of relying on salt. The challenge is to rediscover a healthy balance with this ancient and essential element. As we look toward the future, the story of sodium is far from over. Scientists and engineers are now exploring new ways to harness this abundant and inexpensive element to solve some of our biggest challenges, particularly in the realms of energy sustainability. The same atomic properties that make sodium reactive are now being seen as an opportunity. After powering our bodies, our cities, sodium may soon play a key role in powering a cleaner, more sustainable world. One of the most promising areas of research is in battery technology. The world currently relies heavily on lithium-ion batteries to power everything from smartphones, electric vehicles. However, lithium is relatively rare and expensive. Sodium, on the other hand, is one of the most abundant elements elements on Earth and is chemically very similar to lithium. Researchers are working hard to develop sodium-ion batteries that could be a low-cost, sustainable alternative. These batteries could be ideal for large-scale energy storage, like storing solar power, wind power, for when the sun isn't shining or the wind isn't blowing. Another critical area is desalination, the process of turning salty ocean water into fresh water fit for drinking. Agriculture. As the world's population grows, climate change affects water supplies. Desalination is becoming increasingly vital. Most desalination technologies work by separating the salt from the water. This creates a byproduct, a highly concentrated brine. Finding environmentally safe and economically viable ways to manage this brine is a major challenge. Some innovative approaches are looking at ways to extract valuable minerals, including sodium compounds, turning a waste product into a resource. From advanced batteries, new chemical manufacturing processes, sodium is poised to be a key player in the green technologies of the future. Its abundance and low cost make it an attractive alternative to rarer, more expensive elements. The challenge lies in mastering its chemistry to create efficient technologies, safe technologies, long-lasting technologies. Just as Humphry Davy used the cutting-edge tool of his time, the electric battery, to first isolate sodium, scientists today are using advanced tools to unlock its potential to build a better future. The explosive metal is being tamed for a new purpose. So we are left with a final, profound question. This element can burst into a destructive flame, yet it also provides the gentle spark for every thought we have. It has been a source of wealth for empires, a source of health problems for modern society. It lights our streets and may one day store our clean energy. It is a story of duality, danger, necessity, of the atom, the ocean. As we continue to unlock its secrets, will we learn to master the paradox of sodium, using its power wisely without falling victim to its risks? Well, will we?